Okay, hello and welcome to this video on free body diagrams. Quick question for you. What's a pirate's favorite letter? Is it R? It is, just so you know it is. Okay, um, in this video, here's what we are trying to do. By the end of this lesson, I hope you will be able to draw a free body diagram to show the forces acting on an object and predict a change in motion of an object based on the relative size of forces that you see in a free body diagram. So let's see, what am I talking about? Okay, so here's a question for you. Imagine we're interested in what a plane is doing, right? We got a plane, it's flying through the sky. Is it slowing down? Is it speeding up? Is it climbing or is it descending? Well, one way that we could figure that out is to look at the various forces involved in it. So there's four basic forces involved in an airplane flying. There's the weight, which is the force of gravity. There's drag, which is the air resistance pulling back on it. There's lift, which is what is making it go upwards, and there's thrust, which is making it go forward. So you've got these four forces involved, and depending on how big they are relative to each other, we could figure out if it is slowing down, speeding up, climbing, or descending. So let's take a look at how we might do that. Okay, first, let's just remind ourselves that forces are either balanced or unbalanced. They're either balanced or unbalanced, and motion only changes. Things only either speed up or slow down or start moving or stop moving when things are unbalanced, when forces are unbalanced. And so things can be in motion without any forces applied to them. So this is a good example. These are balanced forces. Notice these arrows are the same length, and we see some numbers underneath them for the actual magnitude of these forces. So it's going 300 newtons in both directions, and so that is causing this rope right here to not move at all. But when the balance no longer exists, when things become unbalanced, it's going to start moving. And so once this, see how the arrow is bigger than it is here, once this gets longer and this gets bigger, this rope is going to start moving in the direction of the larger force. So in order to look at things like that, we use what we call a free body diagram. And a free body diagram shows all of the forces acting on an object at one time. So it just happens to be an example where we're looking at some random object, could be anything. We'll just say it's a box, right? Oh, bad handwriting. But that's a box, right? And what's acting on it right now is the force of gravity pulling down, the normal force of whatever surface it's on pushing back up, an applied force that's somebody sort of pushing on it, and then a friction force that's resisting it sliding across whatever surface is okay. And here's how we draw a free body diagram. So the first thing that we do is we pick the object that we want to analyze. There's some specific object out there. Maybe it's a box, maybe it's a ball, maybe it's an entire airplane that we want to analyze. We're going to just draw a square, a box that represents that object. And then we draw an arrow to represent each force acting on the object. And, this is a key point here, make sure the arrow shows the direction and relative size of the force. Relative meaning that it should be, if there's more force in one direction than the opposite direction, that one where the more force is should be longer and the other one should be shorter. That's how we can use them to figure out what's going on. Here's a first example. So we've got a book. This red rectangle represents a book. It's sitting at rest on a tabletop. What are the forces acting on a book, on that book? So we know that it's at rest, which means that all the forces involved must be balanced. And so I'm going to start off with step 1, identify the object. Okay, it's the book. Step 2, draw a box for that object. So there's the box representing the book. What is acting on it? Well, it's on planet Earth, right? So pretty much always that means there is some force of gravity acting on it. So that's an arrow pointing downwards. I'm going to label it with F little grav. F grav means force of gravity. It's not moving, which means that or I should say it's not changing its motion. It's actually sitting still. That means there's an equal force opposing the force of gravity in the opposite direction. So I need to draw an arrow that's pretty much the same size and label that with what force that is. Well, hopefully you remember that the force that opposes gravity when something is resting on a surface is called the normal force. So F norm for normal force. So we've got two roughly identically sized arrows around this box showing that no motion is changing. Right? Okay, next example. An egg is free falling from a nest in a tree. Neglect, that means ignore, don't pay any attention to air resistance. We sometimes do that because otherwise things might get kind of complicated. Draw free body diagram showing the forces involved. Okay, well I'm interested in this egg right here. That's my first step. And my second step, I'm just going to draw a square to represent the egg. So this is the egg. What is happening to it? Well, it's falling downwards. We know that gravity is involved. So I'm going to draw a downward arrow, and I'm going to label it F grav for gravity. And it's falling, so I know that it's getting faster and faster as it's going down. That's an unbalanced force. Anything that's falling with gravity is actually accelerating. Its motion is changing. So I know that there must be more arrow going down than arrow going up. And if we were doing this in a little more real-world fashion, we might add air resistance, but there is no air resistance because it told us not to do that. So we're actually done right here, right? We've got our egg, and we've got our force of gravity pulling down, and that nothing else, right? There's nothing to indicate that anything is going in any other direction. So F grav, and you know because there's no opposing arrow that is accelerating downwards. Bad news for the egg. Okay, here's your next example. A flying squirrel. Everybody loves a good flying squirrel. A flying squirrel is gliding from a tree to the ground at a constant velocity. Consider air resistance. Consider air resistance. So that means we should add in air resistance. And there's a key here we want to pay attention to, constant velocity, right? Constant velocity tells me that velocity is not changing, meaning that forces are balanced. Okay, so we're interested in the flying squirrel. We're going to draw a box to represent Mr. Flying Squirrel here. And what is acting on him? Well, gravity, right? We're on planet Earth. There's gravity. So I'm going to draw an arrow. I'm going to label it F grav. Usually speaking, we're talking about gravity being involved. What else? Well, it told us to consider air resistance. Is it changing its motion up or down? As far as we know, no. It is at a constant velocity. So I'm going to draw this up arrow, and I'm going to say F air for air resistance. Maybe I could have said drag, but F air works too. Notice they're pretty much the same length because it's about the same force. They're balanced. Right? Is anything happening this way or this way? No. And that's the weird part. He could be moving across, but just because he is moving across doesn't mean there's any force being applied. So the reality is, this is what's happening, and he's moving at this constant velocity this way. Okay, let's try another example. Now we've got the same book at rest that we had in the first problem, but somebody is pushing on it, right? And we've got friction involved. We're going to ignore air resistance. There would be air resistance, but not a whole lot when we're talking about a book. Okay, so here's our book, our badly drawn book. Here is a box to represent our badly drawn book. So what is going on? Well, don't forget, we're on planet Earth. There's gravity. So I'm going to draw my gravity arrow. F grav. And because it's not accelerating up or down, I need an opposing force that's keeping it from moving up or down, and that is the normal force, F norm. Maybe it's the force of a guy named Norm, but really it's normal force. Sorry about the handwriting. Okay, but it is being pushed across, and it's moving across the desk, so it's no longer just stopped. So what we need to do is we need to add that push. As an arrow to the right, it said rightwards. And we're going to say this is the force, and I like to say APP for applied. You know, you're pushing, that's an applied force. And friction is involved. Friction is definitely involved because it told us to consider friction as moving on a surface. So make that big F little friction, or frict, the friction. But notice that's smaller than the applied force. Otherwise, it would either be moving in a constant speed, or it would be not moving at all. But it said it was at rest and started moving. So that means there must be more of this than this. Otherwise, that wouldn't have happened. Okay, so I hope that was helpful. Those are your examples of how to do free body diagrams. Practice them on your own, get comfortable with it, and I'll see you in the next video.